Hello, everyone. So let's get started here with Chapter 6. Chapter 6 is chemical reactions and reaction mechanisms. This is actually where we're really building up our tool chest to be able to talk about chemical reactions rather than learning about specific ones at this point, right? So this is going to be introduction to stuff like thermodynamics, your free energy diagrams, kinetics, the actual arrow pushing, the reaction mechanisms, all these things that will apply to all reactions, so that when we start getting to specific reactions in the future, we have these tools to talk about them, okay? So first thing we're gonna do is talk about thermodynamics. So this is probably a little bit of a review, but nonetheless, thermodynamics is always a really difficult subject, so I'm sure it's gonna be good information for everybody. We're gonna start with this topic of enthalpy. Let me just say, one of the things that makes thermodynamics kind of confusing is because we're always just talking about energy, but energy has it can manifest itself in different ways, right? So, you know, remember from your physics class, you have potential energy as well as kinetic energy. There's electrical energy. There's just all these different manifestations of the same thing that is energy. And on the one hand, we have this very good understanding of energy. Like, yes, we know that it requires energy to lift up a water bottle or, you know, something like that. You got to put in energy to move a rock. But on a chemical scale, things get a little bit more complicated. So there's sort of some main manifestations of energy that we're going to talk about. The first one being enthalpy. Enthalpy is the heat that is exchanged between a reaction and its surroundings. And this takes place at constant pressure. Honestly, I wouldn't get too bogged down on the constant pressure part. But yes, so it's heat. That's what you want to think about, okay? These reactions will absorb heat as well as emit heat. So why does that happen? Okay, so when we're talking about enthalpy and heat exchange, we're talking about bonds being broken and formed. That's the main form of changes in enthalpy that we see. So what do I mean by that? Well, let's just remember here, right? So we have our little bonding orbital diagram here. What does this represent? Remember, so over here, these are the atomic orbitals. So this would represent, let's say, just hydrogen all by itself with its one electron, hydrogen all by itself with its one electron. And then they come together and form that covalent hydrogen-hydrogen bond. Both of those electrons move into a bonding molecular orbital, right? And key is that bonding molecular orbital sits at a lower energy than those atomic orbitals, which means if I want to break that bond, meaning I want to separate those hydrogens back out, I have to put energy in order to do so. Likewise, when that bond forms, it will release energy, okay? And this is done in the form of heat. There's actually two types of ways that bonds can break. There's what's called homolytic cleavage. Let's just sort of zoom in real quick. Homolytic cleavage, which is the bond breaks identically in both directions, meaning one electron goes to one atom, the other electron goes to the other atom. Notice in our arrows, first of all, you have two arrows starting at your bond, and each arrow has just like half of an arrowhead to it. That means to represent just one electron being moved. And they always kind of have this bunny ears kind of thing going on. These will form what are called radicals, okay? So these are unpaired electrons, right? If this bond is going to break homolytically, one electron is going to go onto this one atom, one onto the other. That means there's going to be an unpaired electron. Radicals are actually, so we'll spend some time, I think it's chapter 10, talking specifically about radical reactions. Most reactions don't occur through radicals. They occur through bonds that are breaking or being formed through what is called heterolytic cleavage. So notice now that my arrow is a two-headed arrow, or not a two-headed, whatever, two-pronged arrow, representing the movement of both of those electrons, right? So this is what we're used to seeing, where this arrow here indicates the pair of electrons that was in this bond jumping up and becoming a lone pair on this Y atom, while the X, which was originally sharing that pair of electrons, got it snatched away from it. So now it's left with a net positive charge, okay? This is all reactions that we talk about in organic chemistry are going to be this sort of heterolytic cleavage. These are also called ionic reactions. It's kind of weird because they don't involve ionic compounds, but it's referring to how these bonds are being broken. And notice that those electrons are always then stay paired. Okay. We are going to talk here in a second. Let me just show you the punchline here. We're going to be able to calculate the actual changes in enthalpy in a given reaction using what are called bond dissociation energies. Okay. So just to take an example here, this is hydrogen gas. And if we look here, it has a bond dissociation enthalpy of energy of 435 kilojoules per mole. So what does that mean? That means that if you had a mole of hydrogen gas and you put in 435 kilojoules of energy, you would break those bonds. Now, specifically, going back to this whole idea of heterolytic and homolytic, these bond dissociation energies, they apply to the heterolytic cleavage of a bond. Nonetheless, we will be able to use them to calculate the changes in enthalpy, delta H's, for reactions that don't involve homolytic cleavage. Okay? If you're talking about just breaking the bond, then you have to consider that it's homolytic. But when you're talking about breaking and reforming, it turns out that it's the same whether you consider the bond to be homolytic or heterolytic. It's this bizarre property of enthalpy as well as the other thermodynamic properties we're going to be talking about, which are they are state functions, meaning it doesn't matter how you get to A or B, the difference in energy is always the same. Okay? So it's kind of a little technical aside. I don't know if I'd get too bogged down on it. So first of all, let's look at what is going to be a hugely important kind of thing, which is these energy diagrams. Specifically, we're going to see a few of them. Pay attention to what's going on the y-axis. Specifically, we're talking here about enthalpy diagrams, okay? And what is this showing you? So this is telling you how the enthalpy is changing throughout a reaction. So reaction coordinates, you can think about that as like reaction progress. On the one side here, this represents my starting materials are my reactants. And then over here, we have the products, right? And this is the enthalpy throughout that reaction, okay? And you'll notice that as the reaction proceeds, you first have to climb this little mountain here, right? So this is the energy that has to be put in to break those bonds, right? It will require energy to break those bonds. So this first step is the bond breaking step where you're putting in that enthalpy. And then what happens now, you start careening downhill here. This is the energy that's released when bonds form. Okay, now the gap between where we start and where we finish, this is the delta H, the change in enthalpy throughout the reaction. If you release more energy when your bonds are formed than you had to absorb to break the bonds, you will have a negative delta H, and that's what's called an exothermic reaction, right? Negative delta H, exothermic, that means that the bonds that are being formed were that much more stable than the bonds that you started out with, right? So breaking those bonds required some input of energy, but then when those new bonds formed, a lot more energy was released. So that's an exothermic reaction. The other one, and you know, if you probably remember from Gen Chem, if you're holding a beaker in an exothermic feel is that the reactions causes the surrounding temperature to increase, right? That reaction is putting out heat, and so it's being by your beaker and then your hands that you're feeling, right? The alternative would be what's called an endothermic reaction. So now look that here's the energy that I put in to break bonds, and I only got this much back out when my bonds formed. Right, so the bonds that were broken were stronger than the bonds that were formed. This is what's called an endothermic reaction. If you're holding a beaker and an endothermic reaction happens, you will feel that the surrounding temperatures decrease, okay? And that just means that the reaction was absorbing more heat than it was putting out. And yeah, endothermic positive delta H, exothermic negative delta H. Okay, cool. So now let's work on actually using this table to calculate the delta H for a given reaction, right? The delta H is going to be the sum of the energies of all the bonds that broke, right? How much energy you had to put in to break bonds, minus the sum of the energy that was released when all those bonds were formed. All right, so let's do an example here. So first of all, it's gonna be a simple example, but nonetheless, same procedure as you would use. We have our two compounds, and those are gonna come together to make two. All right, so hydrogen gas and fluorine gas coming together to make hydrogen fluoride, and I'm gonna have two of them. So which bonds are being, let's actually color code this a little bit better. Which bonds are being broken? That would be my fluorine-fluorine and my hydrogen-hydrogen bond. And then which bonds are being formed? Those are these two hydrogen-fluorine bonds. So I'm gonna have to look up these bond dissociation energies for each of these bonds on my table. So that's fluorine, fluorine, hydrogen, hydrogen, and then hydrogen, fluorine, okay? So you want to familiarize yourself with this table, just like our pKa table. The first time around, it's going to be a huge pain in the butt because you don't know where anything is, and then you gain a sense of familiarity with it, and it's not too bad. They're broken down into bond to hydrogen, carbon-carbon bonds, bonds to methyl. This is now going to be like bonds to secondary carbons and tertiary carbons here. So what we're going to be looking for is the bond dissociation energy here. I'm going to work in kilojoules per mole. You could use kcal per mole. It's exactly equivalent. It's just like, you know, measuring in feet versus inches versus centimeters or whatever. Kilojoules per mole. Kilojoules is sort of what I'm more familiar with. If you're like a more biologically oriented scientist, you might like kcals. Really doesn't matter. It's going to come out to the same sort of same thing qualitatively. Okay, so here's my hydrogen-hydrogen bond. Here's my fluorine-fluorine bond. Bond dissociation of 159. So let me go put those in. 159 and 4, what was it? 35. And these are all in kilojoules per mole. I'm gonna get lazy with my units here. And now the new bonds that are gonna be formed are going to be these hydrogen-fluorine bonds. All right, so those will have a bond. If you broke that bond, it would require 569 kilojoules to break. That's also how much will be released when that bond's formed. So we have 569, and then it's going to be times 2 because I have two products. I sort of drew them both out just to make this super clear, but you do want to make a note that, right, you'd have to distribute that to both. Okay, so here we go. I'm going to take my bonds broken and subtract the bonds that are formed. So that means that my delta H is going to be equal to 159 plus 435 minus the 2 times 569. Okay, I don't know what that is off the top of my head. 159 plus 435. So we have 594 minus okay, which means that my delta H for this reaction is going to be negative 544 kilojoules per mole, which is actually a humongous amount, but yes. So anyway, you can calculate using these bond dissociation and, energies what the enthalpy of a reaction will be, how much heat is going to be absorbed or released during the course of a chemical reaction. And we can use this in the future, we'll see. We're gonna plug this in with our information about entropy and free energy in order to determine whether or not a reaction will spontaneously occur. Okay, so practice that, and then we'll move on to these other thermodynamic quantities.